Hi, my name is Nate.
My name is Daniel.
My name is Michaela.
And I'm Alex.
And together we will be talking to you about axial compressors.
An axial compressor is a device used to continuously compress gas in applications with high flow and efficiency requirements, such as in jet engines and some power plant cycles. Here, we see an animation of a simplified compressor where the blades of the rotor and stator are shown. And here, we have a slightly closer look at the shape of one rotor-stator pair, which is called a stage when referring to axial compressors.
Let's start our analysis by taking a look at the fluid flow through a stage of an axial compressor. We find the fluid's absolute velocity at a given point with a velocity triangle. First, we define the rotor's velocity as v. The relative velocity of the fluid, w, is in a reference frame moving with the rotor. Summing these two vectors gives us the absolute velocity of the flow, u. We can apply this concept by looking at the cross-sections of the rotor and stator, with velocity triangles drawn before the rotor, and after the stator.
At the rotor's entrance, the absolute velocity u is approximately axial, so the angle alpha is low. The rotors apply a force in the direction they are rotating, increasing alpha and the fluid's absolute velocity. This is reflected in the velocity triangle at the exit. The rotors are doing work on the fluid, increasing its total pressure.
At the stator's entrance, the fluid's absolute velocity is the same as at the rotor exit. The stators affect the absolute velocity in two ways: decreasing its magnitude by increasing the channel size, and changing its direction with the airfoil's camber. Both of these are again reflected in the velocity triangle. The absolute angle, alpha, changes, and the overall magnitude of u decreases. To facilitate stage stacking, each rotor-stator pair is designed such that u3 equals u1, so the fluid flows smoothly from the outlet of one stage to the inlet of the next.
We will now track a fluid particle through the stages of an axial compressor. On the left, we have a side view of a cross-section, almost like the view in the animation on the first slide. On the right, we have a top-down view of the rotor and stator airfoils. We will simulate the rotation of the rotors with linear motion of these cross-sections. The position of the fluid element is shown in red.
Our fluid element starts at the leftmost rotor entrance and follows the dotted red streamline as the rotor moves. As work is done on the flow, total pressure increases, as reflected in the qualitative graphs at the bottom left. As the fluid travels through the first stator, we see the expected trade-off between static and dynamic pressures.
Once again, the fluid enters the rotor stage and accelerates, increasing in total pressure before the stators convert the added energy into static pressure.
Now, we will derive a first-order approximation of the pressure increase through a single stage. We can use the Bernoulli equation over the stator to find the difference in dynamic pressure between the rotor exit and the stator exit as seen in equation 1. With the assumption shown on screen, we can equate the dynamic pressure decrease over a stator to the static pressure increase over the entire stage, which we show in equation 2.
Using geometric relationships derived from velocity triangles, we can rewrite the pressure change in terms of the axial velocity and the absolute angles. A more precise definition of pressure increase without these assumptions requires knowledge of thermodynamic parameters outside the scope of this presentation.
We can define performance parameters to further characterize the flow. The flow and work coefficients, phi and psi, are useful non-dimensionalizations of the flow rate through the compressor and work done by the compressor, respectively. The degree of reaction, R, is thermodynamically defined, but can be simplified to a relationship between the static pressure increases over the rotor versus the entire stage.
These relationships can be manipulated to fully define the angles and magnitudes in the velocity triangle. This kinematically constrains flow through the stage, which allows us to calculate the pressure increase and the work required to run the compressor.
Finally, the Mach number and Reynolds number can estimate when to expect losses in the compressor. A Mach number below 0.49 ensures no shock occurs in the compressor. A Reynolds number above 10 to the 6 ensures the working fluid is fully turbulent, which prevents flow from separating on the rotors and stators. Separation is especially important here because it would violate basic assumptions of our analysis. Finally, we hope you enjoyed our presentation on axial compressors.
So you can all hear the terrible sound you never want to hear when working on turbine engines.